Hello my dear children of class 11 science. I again welcome all of you through this mode of teaching. We are following YouTube mode, okay, and in today's class we do continue with the chapter that we were doing in the last class also, that is elasticity. So one of the first chapter under unit number 7, okay, and in today's class so we start with the topic, important topic, and the topic is work done in stretching a wire. Work done in stretching a wire, okay, that is elastic potential energy of a what? Wire. Elastic potential energy of a wire. Now this is a topic from where we solve some numericals also, okay, and these are topics which will be asked even in the examination as a derivation also. Sometimes you will be asked to derive the expression of elastic potential energy in a wire, or we can also call work done in a stretching wire, okay. Now you know energy are different types. So one of the type of energy is called mechanical energy, and mechanical energy are also how many types? Two types. One is called potential energy, one is called kinetic energy. But you know potential energy is also two types. One is called elastic potential energy, one is called gravitational potential energy. Okay. Now basically when I take a wire of certain length and area, okay, and if I apply some force along the wire, okay, then what happens? There is an elongation in the wire. Means the wire gets stretched, okay. So once the wire gets stretched, okay, there is a change in the size of the wire. Even there is a change in the size of the wire. Now why it happens is because every wire is made up of molecules, okay. So in between the molecules there is always attraction takes place, intermolecular force of attraction takes place. But when you do apply some amount of force, external force on the wire, okay, so that the wire gets stretched, then we usually do the work. See, we usually do the work against the what? Attractive force. And this work which is done against the what? Interatomic force, or we also call intermolecular force. Okay. But when we do the work, and that amount of work which we do is stored in the form of the energy in the wire, and that energy is called elastic potential energy of the wire. And we are going to derive now this energy called elastic potential energy, but in the form of work done. Now in order to derive the expression of work done in a stretching wire, that is the elastic potential energy in a wire, let me consider there is a wire. The wire made up of any material, okay, but every wire has a length, and that length I consider as L. So capital L be the length of a wire. Now basically this length is the what length? Original length of a wire. But you know children, every wire has area of cross section also. Area of what? Cross section. So I've already considered L be the length of a wire, and okay, let me do continue, and capital A, say I'm marking capital A be the what? Area of cross section, be the area of what? Cross section of a wire. Area of cross section of a wire. Now I'm assuming out here the wire can be of any material, okay, but only thing is that we are considering one is length, another is what? Area of cross section of a wire. Now in order to stretch the wire, okay, in order to stretch the wire you must require an external force. Means we need to apply some external force so that the wire get elongated by certain length. So that force I consider say is F. So capital F I am considering children be the external force. Be the what force? External force applied. External force applied along, okay, let me use the word along the length of the wire. Along the length of the wire. So how much external force that we are applying? F. Now definitely if there is some external force applied on the wire, okay, you will do the work. So we do the work, and we do work against the what? As I said, intermolecular force of attraction. Okay, intermolecular force of what? Attraction. But even doing the work, some amount of displacement, or there is some amount of increase in length of the wire takes place, and that increase in length of a wire I consider as X. So I write down the increase in length. Let me write down this way. The increase in what? Length. Okay, the increase in length of a wire is say X. Just considering this way. So increase in length of a wire is what? X. So the wire is get elongated or increased by what? Length X. So with this quantities which I considered, from here we can always calculate the stress and the strain. See, we calculate what? Stress and strain. And you know, the stress means the longitudinal stress and strain means the longitudinal strain. Because stress and strain are also three types. But the longitudinal stress and longitudinal strain can be calculated only for those substances whose length is large compared to its area or diameter. So wire basically has a length which has large large compared to what? Area or diameter. Okay. So first thing that I calculate is your longitudinal stress. You know, stress is measured by force per unit area. Force per unit area. So how much force you are applying? F. So F is the force. Now what is the area in which the force is applying? A. So longitudinal stress is force by A. Similarly, there is a longitudinal strain. Longitudinal what? Strain. Now longitudinal strain is actually nothing but increase in length by what? Original length. So in length increases by x. Your original length is L. So the capital L is the original length of the what? Wire. Okay. So with this stress and strain, we can always measure one of the property or one of the characteristic of the materials of the wire, and this is actually determined by the term known as Young's modulus of elasticity. So children, remember this, according to Hooke's law, you have learned it, we always measure the modulus of elasticity. But modulus of elasticity are also three types. Okay, one is Young's modulus of elasticity, one is bulk modulus of elasticity, and another is called modulus of rigidity. But for the length, change in the length, okay, we measure Young's modulus of the materials of the what? Wire. And the Young's modulus is given by Y equals to longitudinal stress by longitudinal strain. So as per the definition, children, you know it is longitudinal stress. Okay, longitudinal stress by what? Longitudinal strain. Longitudinal stress by what? Longitudinal what? Strain. So this ratio measure the Young's modulus. And one thing I want to add, Young's modulus is not same for all the materials of the wire. Different material of the wire have different Young's modulus. Okay, so longitudinal stress as how much is F by A divided by longitudinal strain means X by L. So definitely this will be reciprocal. So let me just reciprocal out here only. So it will be F into L, capital L, by A into what? X. So Y is coming F into L, capital L, by A into X. So from here what I do, I'll make Y as the subject. I'll make Y as the subject, just cross multiplying. If I cross multiply, I write down F into L equals to YAX. Just cross multiply this quantity, this diagonally cross multiply. So FL equals to YAX. Okay, so from here what I'll do, I'll make F as the subject. So if I make F as the subject, it will be YAX by L. So this L will go in the denominator. So this is the force which is required to increase the length of the what? Wire. So this is what? This is the force. This is the force required. This is the force required to increase. Force required to increase the length. Okay, force required to increase the length of the wire. Now actually we need to calculate the work done in stressing a wire, and that work done is actually stored in the form of what? Energy. So to calculate the force or work done, okay, there must be a displacement of the wire, okay, but to calculate the total work done, okay, to stress the wire, and the wire we are stressing by a length how much? X. Okay, I calculate work done to stress the wire by a very small quantity, very small length. And this is actually infinitely small length, which tends to 0 but not equals to 0. Even if you stretch the wire by a very, very small length, which tends to 0 but not equals to 0, we have to do the work. We have to apply the force and we have to do the work. So what I do first, I calculate a very small work done to stretch the wire by infinitely small amount. Then to calculate the total work done to increase the length of the wire to X, I do integrate. So children, out here we need to do the calculation, and that is, the calculation is done on the basis of integration. So I have taught this part. Integration is also called addition or summation. To add up small quantity to get total quantity, we need to do what? Integration. So children, as I said, I calculate a very small work done, and that work done to stretch the wire by an infinitely small length, and that small length is dx, which is also very small, and that is given by dw. And this work done means force into displacement. You know work done means what? Force into displacement. The force applied is F, and the displacement is what? Dx. So in the expression of this work done, I substitute F equals to YAX. See, I replace F by YAX by L, and there is already dx. So these are very, very small amount of work done. But to calculate the total work done now, to stretch the wire from its original length to the increase in length x, okay, so I do integrate this equation. So let me just give this as equation number 1. I do integrate to get the total work done. Now to calculate the total work done, children, in stretching the wire from say x equals to 0, when x is 0 means the length of the wire will be, there is no elongation of the wire, okay. But if you increase the wire length from x equals 0 to x equals to L, so I consider small l is the length which is increased by, the wire which is increased by, wire which is increased by length L, okay. That means x is the variable which changes from x equals 0 to x equals to L. It's always given by, integrating equation 1, both sides. So integration means, this is the sign. So I do integrate this way, integration of YAX by L dx. But remember this, on the right hand side your variable is x and is varying from 0 to L. So x is the variable which is varying from 0 to L. And in this integration, this 0 is called lower limit. And this L is called what limit? Upper limit. So this is one of the calculus called integral calculus. So now I need to do the integration. And children, before I do the integration, I use the formula d integration of dx means x. And integration x to the power n dx means x to n plus 1 by n plus 1. So these two formula I have already taught in one of the chapter. Okay. Now let me apply this in this expression. On the left hand side it is dw, and this dw is similar to dx. So integration dw will be w. Just following this one. Now on the right hand side your variable is x only, so other quantity are constants. I'll take out from the integration. Y, a and L I'll just take out from the integration. So inside the integration it is 0 to L x dx. Now I do integrate on the right hand side, so but this right hand side is similar to this expression. If there is no power means 1, so if you compare, then this n equals to 1. So let me expand in this way. So it will be YA by L is already there. So x to the power 1, I write down this as x to the power n plus 1 means 1 plus 1, which is 2, divided by n plus 1 means 1 plus 1 means 2. So I have done the integration. So after the integration you have to put the limit in the bracket. Upper limit and lower limit. Upper limit and lower limit. Now I expand this by writing that upper limit minus lower limit means x is L upper limit, x is 0 lower limit. So it will be YA by L. Look at this part, children. So 2 I'll take out from the bracket. So it will 1 by 2. So x will be now L square. So x means L square upper limit minus x is 0 with square means lower limit. So always expand as upper limit minus lower limit. So this will be YA by L 2L into L square minus 0 means L square only. Now I just rearrange this expression and I write this way. So I'll write 1 by 2 separately. Okay. Then after I write on Y. Then this L square I'll break and I'll write on L. And this L I write by L. Now A is there. A is already there. Okay. Now what I do, I write L. Okay. This L square means L and another is also L. Now there is only one L, capital L in the denominator, but I multiply by L in the denominator and also multiply by L in the numerator. So children see L, this capital L I added and multiply and divided in the numerator and denominator, where there is already L and L. So L square I break as L by L into L. So one L is with capital L and small l, another small l with capital L. Okay. Now the reason which I am doing this way is to express the relation in the form of expression. So look at it. It will 1 by 2. Now why L by capital L means actually a stress. This is your stress. Small l by capital L means strain. This is your strain. And lastly, area into length is your volume. This is the volume of a wire. So area into length is your volume. L by small capital L is your strain, and this is your stress, which means work done in stressing the wire or in potential energy stored in the wire is given by half strain into volume of the wire. And the same work done is always stored in the form of